Okay, hello everyone, and welcome to this week's PhD seminar. Delighted to have Yiyong, who's going to be talking to us about econometric modelling with high-dimensional data.
Yeah.
Over to you.
So hi everyone, my name is Yiyong Luo. So today I would like to talk about econometric modeling with high-dimensional data. Firstly, I would like to introduce my supervisors, Professor John Griffin from our department and Dr. Brooks Page from the AI Center of Computer Science Department. So for the structure of today's talk, I will firstly introduce what is econometric, and then I will focus on the two research topics that I did jointly with my supervisors. So, what is econometric? Yeah. Okay, so since we are working on macroeconomic data, we usually store the macroeconomic data using time series. And the econometricians usually care about two things: prediction and structure analysis. And I will demonstrate what is prediction using a timeline here. So currently we are at this point, March 2024. So if we would like to predict something in the future, then it is just a forecasting, pretty straightforward. But also econometricians would like to know what is the current situation, for example, in the UK. So then we need nowcasting. Similarly, since the data in the past may not be released immediately, let's say in December 2023. So we need to use data up to March 2024 and backcast the data in December 2023. So these are the three categories in the prediction of econometrics. And I will focus on the forecasting because for nowcasting and backcasting, you actually need some different model structures. The second thing is structural analysis, such as impulse response. We can also measure the uncertainties using some index and to decompose the variance of a particular variable given some other variables. I will give you some more detail about this impulse response. So it is the effect of some exogenous shock to the economy. So we would like to quantify this effect and to see how it transfers over time. And I will take an example as the monetary policy shock. Let's say in the current UK inflation rate, it is higher than the target value, which is usually 2%. So the central bank, Bank of England, need to get a like contraction monetary policy to have a positive shock to the interest rate and tamp down the inflation rate. And you can see here we have a curve corresponding to the effect. You have the horizontal line as the timeline and the vertical, the y-axis as the effect, how we measure the effect. You also have a credible interval to show you the uncertainty. So if you have a positive exogenous shock to the interest rate, so here is the federal funds rate, which is the interest rate in the US, but it is the same thing. You have a positive shock, so it starts from 1 and it will gradually come down to 0 because of this positive exogenous shock. And there are two trends for to drive our study. They are the high dimensional data because we have reached to the big data era, and we have, let's say, some global regional data as well as the disaggregated and the aggregated data. So we have a lot of data. A lot of researchers has also showed that it is beneficial if we have a larger amount of data. So how we can deal with this amount of data is one question to ask. Another thing is nonlinearity. Starting from you put some time variation to the parameters. We can also do some non-parametric model structure, such as the Kelly and the Griffin paper about the initiate process and the Hockenberger paper about BUT, which is Bayesian additive tree regression tree model. And Kleiber also worked on some deep learning techniques. So, and we have encountered some problems because of these two trends. The first thing is overfitting, because we have more data, naturally we have more parameters to infer. So overfitting is something that we need to mitigate. How we can model the high dimensional data is another question. Since I am working on Bayesian inference, whether we can find some efficient sampling method is also something we would like to investigate. And after modeling and inferring our model, how can we interpret the results? So I will try to answer these questions in today's seminar. Let's move on to the first research project focused on vector autoregressive model, or you can call it VARB model. It is just a way to model the multi-dimensional data. You have some multi-dimensional data YT, and it is linearly related to its lag values or the past values, YT minus 1 to YT minus P. And they are linearly connected by some matrices A1 to AP. If you stack these matrices together, then you will get coefficient matrix A, like all the linear regression model. And also you will have an error term with usually a normal variable following normal distribution with zero mean and a covariance matrix omega T. And it is widely used in a lot of research fields such as econometrics, finance, neuroscience. For the Bayesian inference, you can just use give sampler to infer this coefficient matrix, given some observed value. It is proportional to its prior and its likelihood. The problem of VAR is that it is prone to be overfitted because the number of parameters grows projectively with the number of time series. And there are mainly two strengths to mitigate overfitting. The first one is regularization, such as lasso and rich. If you are working on Bayesian inference, you can also impose some shrinkage prior. For example, Minnesota prior is really popular in econometrics. Non-gamma is a prior proposed by Jim, and horseshoe is also a prior pretty popular at the moment. But I will not talk about either regularization or shrinkage prior in today's talk. I would like to introduce you a state-of-the-art model called TensorVAR. So firstly, what is tensor? You must have seen tensor in your research lab because matrix has 2 dimensions. So it is a second order tensor. And let's take a look at this structure. It has 3 dimensions. So you can call it a third order tensor. And if you worked on some deep learning project, you must know what is TensorFlow. So data are stored in tensor. So now we know what is tensor, then what is TensorVAR? Let's take a look at the left-hand side of this figure. You have your coefficient matrix and stack all the matrices A1 to AP horizontally. You can tensorize this coefficient matrix by adding one more dimension to the parameter space and stack all the matrices, the submatrices A1 to AP in this direction. So now you can get a 3D structure. You can do the other way around to turn the 3D structure back to your coefficient matrix. So this is the tensorization and the matrixization. After writing the your coefficient matrix in terms of a tensor, it's denoted as curly A. Then you can write your mathematical expression like this. So bracket 1 means the matrixization. In my research project, I actually add another term, which is the on-lag matrix, but it is not the focus of today's talk, so you can just ignore it. I write it just for completion. So far, the number of parameters in tensor curly A, or this coefficient matrix A, is the same. So it is n squared times p. But since it is a tensor, we can actually decompose it using perfect, let's say perfect decomposition, which is a really simple way to decompose your tensor and reduce the number of dimensions. So here is our curly A, and assume that we can predetermine its rank, capital R here. So curly A can be decomposed to the sum of R number of tensors curly AR with the same dimensionality. And this curly AR can be further decomposed to 3 matrices with this dimensionalities. And the ij case elements, the product of these ij case elements can form the ij case elements in curly AR. If you feel a little bit confused about what is perfect decomposition, it is totally fine. The only thing you need to know is that this curly A will transform to capital R sets of vectors, and each set has 3 vectors. This is the only thing you need to know. And here is some terminology. We call the elements in beta vectors to be margins. Let's take a closer look at these margins. If you stack them horizontally with respect to the subscript, then you can get 3 matrices, B1, B2, and B3, and they have different meanings because the H row of B1 corresponds to the effect from the whole economy to a particular variable. Similarly, you can do the other way around. Each row of B2 is the effect of a particular predictor to the whole economy. And you can see for B3, it has it has P rows. So each row is the effect of a particular lag to the whole economy. So they have different meanings, and I call them response, predictor, and temporal loadings. If you stack these matrices together, you can get your new parameter space B. And let's move on to the Bayesian inference of TensorFlow. So you will change the standard Gibbs sampler from getting the posterior of the coefficient matrix A to get the posterior of the matrix B. So it will turn to the unit prior for Bj and its likelihood. If you rearrange the terms, this one is just a linear regression, and I will talk more detail about the prior of Bj later. So then the number of parameters in B will change to this term. Let's take an example. If you have the 40 number of time series and set the lag order to be 3, then you can reduce the number of parameters from 4,800 to 249, which is pretty stunning. But we need to set this rank value to be 3. And this value is pretty reasonable, and I will show you why later. Okay, so now we need to predetermine this rank. What if we don't know any prior information about this rank? What we should do? If you think it in a Bayesian perspective, you can set some prior related to this R and then get the posterior of R. So I set this prior, which is the prior of Bj, because the column numbers in B1, B2, B3 are all capital R. So if we set the prior to Bj, we can directly get some information about R. And what is this prior? We can consider the multiplicative gamma prior, which is the prior we used in our research project. So each margin, the elements in the decomposition, will follow a normal distribution with a variance. And this variance is the product of two terms, tau R, which I will get back to it later, and a local parameter phi. So for this tau R, you can see the reason why multiplicative gamma prior has this name is because the tau R is a product of some gamma variables, delta L. And if the expectation of delta L is smaller than, if it's greater than 1, then the expectation of tau R will increase with R. Naturally, you can think the inverse of tau R will decrease with R. And we call it the multiplicative gamma prior is from the family of an increasing shrinkage prior, because the shrinkage level of the margins with higher column index will be higher. So if the margin is around here, then it will shrink to some smaller value compared to the margins that is here. So we have our prior, but if we initialize an R value to a really large value and run our Bayesian inference, the problem is that it is time consuming. So we need something that to reduce the computational cost. One thing is to do adaptive shrinkage, meaning that we still initialize R to be a large value at the beginning of our inference, and then we will take the criteria to see whether each column in B is redundant or not. If it is redundant, we just remove it, but if not, like we don't have any redundant columns, then we add one more dimension or one more column to B. And after doing this way, we can reduce the value of R to some lower values and make to accelerate the inference. So far,
so can I just start? So this R, so this the rank of these matrices. Does this correspond to the lags in your auto regression, or when you go sort of back to the auto regression, what does that correspond to?
Yeah, so lag order is this P here. So R is something that we actually have no idea. So we have a range of R, but actually we don't have any prior information about it. So
it's just to do with that decomposition.
Yeah,
There's no sort of physical meaning.
Yeah, it is similar to the rank decomposition. If you consider the matrix decomposition, you also have a rank. but the definition of the rank in tensor and matrix is slightly different. So let's move on. So far we have the prior as well as, oh, I see a chat. Is there anything? Yeah. So far we have the prior as well as our Bayesian inference. But if we directly use this Bayesian inference, the problem is that we don't have good mixing. So good mixing actually matters because we need to have guaranteeing the mixing of coefficient matrix, which is this tensor. And the margins are also integrable. So if we have Markov chains of margin doesn't mix well, then we can't interpret the results. So you can see the top panel here. They are the trace plots of our margins, but none of them has good mixing. So we need some strategies that give us the mixing like in the bottom panels. And this strategy is called interweaving algorithm. So the full name is Ancillarity Sufficiency Interweaving Strategy, or ASIS, proposed by Yiyong Luo. Basically, you have two data augmentations, ancillary and sufficient data augmentations, or you can call it parameterizations. You firstly start the sampling from just the one of the parameterization, either of them, and then rearrange the terms or modify your parameters based on the second or the alternative parameterization. Then resample the same set of parameters using the alternative parameterization. I know it sounds really vague, but I will show you later in the algorithm, and then it will be easier for you to understand. So this ASIS strategy has been applied to some econometric studies, such as stochastic volatility and factor models. But instead of using just the two parameterizations, we actually apply 4. What are these 4 parameterizations? The first one, you can consider it as the base parameterization. It is just a prior. But for the rest parameterizations, it will have some different structure. So let's denote B1, B2, B3 as the decomposition of your coefficient matrix. And you can actually modify this decomposition by multiplying diagonal matrix to B1, let's say, and multiply the inverse of this diagonal matrix to B2 to get another matrix B2 star. So after having this multiplication, actually the composition gives you the same coefficient matrix. So they are equal to each other. So what can we choose this B1? There are actually infinite choice for the diagonal terms of B1, but let's set it to be the first row of B1. So then the first rows of B1 star will be just 1. And the rest elements in B1 star follows this prior. So we still have our variance like this one, but because it multiplies the inverse of B1, you need to divide this variance with the corresponding elements in B1. Similarly, for the elements in B2 star, since you multiply B1, this diagonal matrix, to B2, then you need to multiply something after this variance, the original variance. Similarly, you compare B2, B3 to get another decomposition, and B1, B3 to give you parameterization 4. So they are these 4 parameterizations, and we can apply it in the ASIS algorithm. So this algorithm is pretty long, but you can divide it. Let's firstly focus on the steps without any star risks. So they are the step A, C, and E. It is just a standard gift sampler. You sample your parameters B1, B2, and B3 using the base parameterization. So you don't use the rest 3 parameterizations. And let's move on to steps with 1 star risk. So you need to multiply your matrices by something that I have showed you before, these 3 major parameterizations. So you can determine B1 and B1 star and B2 star. For the steps with 2 star risk, then you need to sample the same set of parameters. So they are B1 and B1 here. They are the same. So you need to sample the same set of parameters from another posterior by applying the second parameterization. If you would like to sample B1, similarly, you sample B2 and B3 using the alternative parameterizations. Here is the algorithm. and we can move on to some simulation study. So here I firstly would like to see whether our multiplicative gamma prior, which is this MGP, works. I have 3 scenarios with different number of time series and the true ranks. And you can see here is the competitor called MDGDP, which is another prior usually applied to the tensor structure models. And we can see that MDGDP will give us the true rank, but MGP actually gives us the rank with lower value compared to the true value, but not sacrificing any accuracy. And since we are using adaptive shrinkage algorithm in our MGP, so the running time will be much more lower compared to the one using MDGDP. We can also check the effect of interweaving strategy. So on the left panel, you have the tree plots and autocoloration using interweaving. And on the right-hand side, you have the ones without interweaving. You can clearly see that the tree plots, the one using interweaving, has much better mixing structure. And the autocoloration, if you take a look at this panel, the one without interweaving and use normal prior, then its autocoloration will not decay after 200 lags, meaning that the autocoloration is really high. So you can clearly see that the interweaving strategy is effective. Another way is to check the inefficiency factor, which measures how efficient your algorithm is for different parameters, B1, B2, and B3. So the higher the efficiency factor is, the less efficient your algorithm is. So you can see here, I have the box plots for different priors, normal, MGP, and MDGDP. And the scene before the priors is the I and M, corresponding to with interweaving or without interweaving. It is clear to me that the median of each box plot are lower compared to the median without interweaving, even if sometimes we have some outliers. Each outlier in the interweaving box plots are actually lower compared to the upper whisker of the box plot without interweaving, meaning that our interweaving algorithm is doing its job.
How are you defining that inefficiency factor?
Yeah, so it is related to effective sample size. So you just divide the effective sample size to your iteration, the number of iterations. So it is actually pretty straightforward. But yeah, so we saw that in some ASIS paper, they use this measurement to measure the efficiency. Okay, so let's move on to the real data application. Firstly, is the forecasting performance of the point forecast. I used the 40 features as mentioned in our example using the McCracken paper. So this one has stored the US macroeconomic data. The first 2 models are the ones using tensor structure, the tensor bar model. And the rest 3 are the standard bars using just some priors, such as Minnesota and the normal gamma I just mentioned. And the horizon means like how early you forecast your data. So if the horizon is 1, it means you forecast like 1 period ahead. If it is horizon 4, then it means you forecast 4 periods ahead. And I use the relative mean square forecast error as the metric to assess the forecasting performance. And you can see that the tensor structure actually gives us some really competitive results. You can also check the density forecast. I use the average log predictive log likelihood here. And the tensor bar also gives us some really competitive results. And you can see for the joint one, it's the tensor structure will give you the best performance. Some other variables, you can also check some highlights here corresponding to the best model. And let's move on to the interpretation. So as I mentioned, in the tensor bar model, you can actually call the loadings to be the B1, B2, and B3 to response, predictor, and temporal loadings. And you can interpret these margins using each columns in these loadings. Let's take a look at the first column. So you can see a lot of margins are highlighted as important in the first columns in the response and the predictor loadings. because of the nature of multiplicative gamma prior, since it has the increasing shrinkage property. And some of the variables actually has higher values in different loadings. For example, the response loading, some variables are higher in the coefficients, the margins are higher in the real activity, employment category, as well as the money and credit category. But for the predictor loading, you can see the values with higher, the margins with higher magnitudes are the ones from the employment category, interest rates, and money stock. So it is really consistent with the economy, our current economy in the US. For the second one, it is harder to interpret, so I will just skip it. But for the third column, it is just describing the interrelationship within the interest rate category. So which is something that's pretty interesting because interest rates is usually like correlated with each other, and it can separate the effect compared to the first column. Let's move on to the temporal loading. You can see only the first leg is said to be important, but if we take a look at the ones in the third column, it is also pretty large in the magnitude. I will have some discussion for the first research project. Here are some future work. We can also consider the same algorithm using higher dimension in the tensor. I mean, we currently consider the third order tensor, but it actually can be fourths, fifths. So whether we need to change our Bayesian inference or they stay the same. So this is one question to ask. We can also set the margins to be time varying by having a random walk of margins, and we also need to construct the Bayesian inference based on the time variation. The third thing is to generalize the tensor decomposition. Currently, we use perfect decomposition, but actually Tucker is a generalization of perfect. But we also find that there is some issue if you directly using our interweaving algorithm to the Tucker. So for our second research project, I will focus on deep learning because my secondary supervisor is from the AI center, so why not? But deep learning is actually pretty difficult to be applied in macroeconomic data because usually you store the data in monthly or the quarterly basis, not like, let's say, financial data. You store it like within seconds. So how to make it practical is one question. And the second thing is that so you can see in my first research project, it's mainly about statistics. But for the second one, we would like to make it more macroeconometric. So for our second research topic, we focused on a model called factor augmented bar. It is still a variation of bar because in the second equation, you still have the bar structure. But instead of putting all of the observable variables into this bar structure, we only put a fraction of it corresponding to this YT. And YT will have a lower dimension compared to all the observable variables we used in the model. For the rest term, it is the factor model, the factors FT. So factor also has a low dimension. And by stacking FT and YT, you can get a multidimensional structure and use your VAR model to infer them. How we can get this factor is to extract it from some high-dimensional data XT. So we can use principal component analysis, PCA, to extract the factors, or we can consider these two equations as a state-space model and infer it using comma filter. One question to ask is how can we improve this model during the recession periods? So I demonstrated recession periods using this figure. Here is the unemployment rate I extracted from the Federal Reserve website, and each gray band, I'm not sure whether you can see it is gray. So yeah, each gray band is corresponds to one recession period. You can see here is the financial crisis, and this one, which is pretty narrow, is the one for the COVID-19 pandemic. You also have something like the oil crisis and the stagflation in 70s. So how can we improve the model? And you can see, let's say this spike here, it's really difficult to use the current model. And you can also see this unemployment rate at a peak. It is lower compared to this spike, but you can see this recession period is wider compared to, let's say, this one. So how we can model this kind of structure? One really simple answer to it is non-linearity. So we consider two types of non-linearities. The first one is time-varying parameterization, meaning that we set some parameters to be time-varying. So this model has been proposed by Corabilis 2013. We only set the parameters in var as time-varying, because if we set the loadings to be time-varying, then we have some identifiability issue as well as the overfitting issue. So we just said this, and this is exactly what Corabilis did. For the covariance matrix, we have a class B decomposition to set this HT to be lower triangular matrix, and this ST is diagonal matrix. Here are some more details about the time-varying parameterization. Oh, yeah, I forgot to mention the second type of nonlinearity, which is autoencoder. So instead of using PCA, we use autoencoder. So Kleiber used the time-invariant BAVA model using autoencoder, but we applied both nonlinearity to see whether autoencoder can still play an important role in our modeling.
So can I have a question
Yeah.
about A? The A includes some parameters.
Yeah.
And also depends on T.
Yeah.
So depending on T, so the parameter also change.
Yeah.
Okay.
Yeah, the parameters will also change. Let's say before the global financial crisis, you might have some parameters have some value different compared to the one during the global financial crisis. Yeah, so let's give some more details about the TVP BAVA and autoencoder. So for the TVP, we set it to have some random walk structure. Here is the vectorization of our coefficient matrix A and the non-zero elements in the lower triangular matrix HT. Since ST has some positive value, so we need to take note to get the random walk. For the random walk, here is the covariance matrix, and we assume that there's no correlation between, let's say, AT and HT, and so on. You can get the inferential scheme in the Pursery 2005, which is the paper about TVP VAR model, not BAVA. And for the autoencoder, if you are not really familiar with deep learning, it is a way to compress the high dimensional data corresponding to your input here to some lower dimensional data or representation, or you can call it bottleneck or code. So this procedure, the compression step, is called encoder, and you need to train a model by reconstruct your input to the output. So this structure is called decoder. So after comparing the output and the input, you can train a model. I know this sounds really simple if you know deep learning, but the reason is that we don't have a lot of really nice research using deep learning in econometrics. So if we would like to have some really rigorous study, we firstly need to have some really simple model to show people that it works. For this real data application, we have some higher dimensional data compared to the first research project. We have 169 US economic time series, still extract from McCracken, and we set the YT, which is the thing we will put into the VAR, to be three-dimensional. It has GDP deflator corresponding to the inflation, and unemployment rates, federal fund rates, which is the interest rates that the central bank Federal Reserve need to change in order to tame down the inflation. And the rest time series will be set into XT. So the elements in XTs can be categorized to 5 categories, and I will not give too much detail about it. So the dimension of XT is said to be 3, but after using cross-validation, you can get some different values. This is just some demonstration. For the autoencoder, you also have some architecture, still pretty simple, but we actually need to add some more structure to it. I didn't include it in this talk, but yeah, I'm currently working on this. firstly, after training our model, we can compare the correlation between factors and some selection of our variables. Two things worth noticing. The first one is in this factor 2. So you can see it is grouped by itself. Compared to autoencoder, each factor is grouped by with some different variables. And the second thing is because of the nature of PCA, you actually need to order your factors with respect to the eigenvalues, right? So if you take a look at this third factor, the correlation between the third factor and some variables, you can see the color is lighter compared to the other two factors, the factor 2 and the factor 1. And I have some figure in my research project, but not in this talk, to show you that in autoencoder, you will not have this kind of issue. The scale of correlation always stays the same. Yeah, we don't have a lot of time, so yeah, let me move on to the impulse response. So here I studied the expansionary monetary policy, meaning that we have a negative shock to the federal fund rates. One thing will, so yeah, the curve, the solid curve, and with that blue band is for the one using autoencoder, and the one with dashed curve and the gray band is for PCA. And you can see for inflation, we have a thing called price puzzle, meaning that if you have an expansionary monetary policy, the this curve would just immediately, or let's say, increase at the first period and just directly increase its value, but not like the dashed one, which will further decrease and then increase again. So this kind of phenomena is called price puzzle. And we see that using autoencoder, we don't have this issue. So at least the solid one doesn't have the price puzzle issue. The second thing is that the credible interval of the one using autoencoder is always narrower during the recession periods. For example, this oil recession and financial crisis in 2008 and 2020 for the pandemic. I don't have too much time to show you the impulse response to the XT, so I will just give it. Okay, so here are some forecasting performance. Each column is one variable and each row is a horizon. And we have, here is the third horizon, which is the highest one we have. And you can see the benchmark is the one without any nonlinearity, the time invariant model with PCA. So, and we can see that as the horizon gets higher, then the one using autoencoder, both nonlinearities corresponding to this orange one is getting the higher value in the density forecast. Similar thing in the unemployment rate, especially during the pandemic. We don't have the similar kind of performance in federal fund rates, and this is something that we would like to improve. I will wrap up my talk here. In the first research project, we focused on TensorVar, and we worked on some Bayesian inference of TensorVar. The original paper is using some frequentist method, so we are working on Bayesian. TensorVar is a way to mitigate overfitting by setting the rank value, and we can reduce the number of parameters. For the nonlinear FAVA model, we consider two kinds of nonlinearities. FAVA is already a model to elevate overfitting, and we have showed you that using nonlinearities seems to be a good thing for FAVA. Here are some bibliography if you would like to know more about my work. And thank you for your listening.
Wonderful, thank you for the talk. I think we've got time for a couple of questions, either online or in the room. Yeah.
Great, thank you. At the beginning, you said that you've chosen R to be 3.
Yeah.
So this is the number of loadings.
Yeah.
And then, of course, in that first application, we saw that that first loading gets really a lot of weight, with the next two having much smaller weightings. Is this an artifact of the shrinkage prior, or if you had more loadings would a higher R, would more loadings get more weight, or is your prior just incredibly strict?
Yeah, so you're saying basically this interpretation, right? So for this one, it has some increasing shrinkage property, and the first column is having some higher magnitude compared to the others. So yes, it is the artifact of the multiplicative gamma prior. Because of this increasing shrinkage property, we can infer the rank. And unfortunately, it will give you some lower and lower kind of the variance for higher columns. So there are some other kind of methods that you can apply to remove this kind of issue. But current project will only focus on multiplicative gamma prior.
Sure, but I mean so much of it as being an issue is the weighting invariant to the number of columns you start with, is what I mean. Like, if you made R 5 or 10 here, would you still have all of the weight in that first loading?
Oh, I see. Yes, so if you set the prior to be the same, then the weighting in the first column will still be the same.
Okay.
Yeah.
Any more questions in the room? So I had a brief one with the interweaving steps. I was wondering if you could provide potentially just a little more intuition about how adding these steps is sort of fixing the mixing problems, how maybe sort of some of the pathologies which are sort of in the sort of standard steer, and then how the parameterizations fix those.
I see. Yeah, this is actually one thing I would like to add into my talk, but I think I don't have enough time, so I just give it. So for the Gibbs sampler, let's move on to this one. For the Gibbs sampler, you can see BJ, let's say B1, will depend on the updates of B2 and B3 in the last iteration in our MCMC, right? So, and then it is the same. You sample B2 given some other parameters and B3. But if you move on to the next iteration to sample the B1, then it depends on the last iteration, right? But they also sample depends on the last iteration, the B1 in the last iteration. So that's why you have the autocorrelation. So we need to just detach this kind of connection by having two parameterizations. So in our interweaving step, which is when we construct these parameters, so basically we're just like cutting this kind of connection between B1, B2, and B3.
Thank you. Any final question?
I've got one more. When you're doing the deep learning steps, is it Bayesian deep learning, or are you just kind of doing it standard SGD?
I see. Yeah, we didn't do Bayesian, just the really simple gradient descent. The reason is that so for some macroeconomic paper, they actually have Bayesian deep learning, but it is pretty like complex because they will use some shrinkage prior, as I mentioned, the Minnesota and the normal gamma. It's actually, I don't think it's really practical. So that's why I only use the gradient descent, so that somewhere in the central bank, the researchers can actually use my model.
Does that mean, sorry, when you say they're using Minnesota, are they somehow nesting the Minnesota into the neural network?
It really depends on your model, actually. For this one, I don't think I will use Minnesota, but yeah, because of the deep learning, you will have a lot of parameter rights. So for the people in macroeconomic, if they come from a Bayesian background, then they will apply some other priors, such as the spike and slab.
I think that's our time, so let's thank the speaker once again. And we'll be back in 2 weeks for the final talk of the term, which will be given by Ilse. Thank you very much.